Okay, we're moving on into volume now. We're going to look at what methods or what approaches that we can utilize or use to calculate volumes. Okay, as introduction, let's look at those pictures. Basically, just to show you, whenever there's a civil engineering project, okay, normally there'll be some earthwork involved, whereby earth or soil will be excavated, excavation activity, and having done that, the soil or the earth will be loaded onto a vehicle or lorries for transportation and to be sent somewhere for backfilling. And at the site, we will have machines to do some grading to get the proposed level that we require. And whatever material that we don't need in the construction will be disposed of somewhere, and there'll be dumping. So all in all, in this activity, which is I've shown on the screen, there are other activities, but I've just shown the main ones here. Will involve dealing with volume of material, volume of soil. So that's why that's the basic reason why we need to be able to do some estimation or to do some calculation. Okay, so when it comes to any civil engineering project, it normally entails excavation, backfilling, dumping of soil, which we call as term as earthwork in general. And since we're dealing with soil, amount of soil, so we have to be able to make good estimate. Okay, I purposely use the word estimate here because we cannot. It's not an exact calculation when we're dealing with earthwork. So we could make the best estimate. So trying to minimize error, so to come up with the best value. So the best estimate. Okay, and we also sometimes if we happen to be involved in dam design or dam construction, reservoir, we might need to find out the capacity of the water within the reservoir, probably. And if you are working in quarries, maybe power plants where you're dealing with spoil heaps, okay? And you also might need to come up with the volume from time to time. Okay, so excuse me. Volume calculation methods that we can use depends on the type and the nature of the construction. Okay, there are in general three types or three approaches. We could use cross sections, we could use spot heights, or contours. Okay, so what is what? Which one is suitable for what? For what purpose? So cross sections, basically, if looking for constructions that involves alignment, road and railways, pipelines, channels, and etc. That could be a stormwater drain. Okay, where we'll have sections along the construction. So cross section will be the best method to use when we want to calculate volume. If the construction is localized, say a shopping center or a tank, underground storage, okay, open pits, okay, either like a basement, probably storage or open pits. So it's a localized construction. So spot heights method might be the best solution to it. Okay, the best method to use to calculate the volumes. And on the other hand, if you're dealing with large areas like reservoirs or dams, okay, we want to calculate or we want to obtain the volume of water contained, or when we're looking at probably reclamation work, we will be putting soil into the sea to come up with new land. So that will be contour will be the best, the most suitable method that we employ, okay, to come up with the volume that we require. So let's go to the first one. Okay, volume by cross sections. So what I have there is basically a cross section, okay, that cross section there, and I have one cross section, the first cross section, which is the area there, call it A1, okay, and I have another cross section, and let's use a different color. Let's use like cyan. Okay, I got another section at the back here, and let's call that A2. Okay, if those two sections are separated by a distance L, okay, the separation between them, so the volume is simply given by that. Okay, the mean of those two areas, A1 and A2, so the mean, okay, multiply by the distance L, so that will give me the volume. So if I have a series of chunks like this, okay, series of chunks like that, I will have a series of cross sections, and if they are all L meters apart, then I can come up with a general equation, which is similar to the trapezoidal, if you remember, in our previous slides. Okay, so that's cross section by n areas method. Simply means you take the area of both ends, mean them, and multiply by the length. Okay, next is a volume by cross section using prismoidal method. Okay, so again, we have one cross section there, the first cross section. We have a second cross section which is somewhere midway, okay, which is that one there in this case, and we have one last one at the back, a cross section, which is that one there. Okay, so we have three cross section, A1, A2, and A3. So what we're going to do is we're going to use both these chunks, that one and that one, to calculate the volume. So just given by L, that distance there, distance between each chunk, A1, 4 times A2 plus A3 divided by 3. So if you look closely to that, it looks similar to the Simpson method in calculating area. Okay, so this particular approach is called the prismoidal method, and if you have n cross sections which are L meter apart, you can use that general formula. Okay, again, n must be odd, similar to Simpson. N must be odd. If it's even, try to use prismoidal to the last section, the odd last section, and the remaining section will use your n areas method. Okay, so basically prismoidal should be preferred over n areas if possible. Okay, all right, especially if the distance L is quite large. Now, the second approach of calculating volume is using spot heights. Okay, as I said earlier, when the construction is localized at one particular spot, shopping centers, and then building a shopping centers, a stadium, a housing estate, and then something similar. So spot height will be the best approach to use. So what we do is we will create a grid. We will form a grid over the area, And we will determine the reduced level of the grid points, intersection of the grid points. And we're going to look at the differences between the height of the grid points, the existing grid point, or the grid points on the existing ground, and the proposed level of that point in question. Okay, I think I have a figure. That's to show you, okay, what I mean by that. So let's assume the green area here, okay, there is an existing surface, okay, and I have produced a grid, okay. I've measured grids along on the surface, okay, which I projected onto the purple or the magenta figure there. Okay, let's look at one cell, that one there. Let's look at A1, okay, the cell 1 here. So let's look at that cell. I've got a grid area, A1, and I've got heights differences, H1, H2, H3, and H4 are the difference in height between existing point or existing reduced level there and the proposed reduced level there, okay. So the difference between existing and proposed, so that gives me the little h1 to h4. So to calculate that volume, we simply take the mean of all those differences, which is h1, h2, h3, h4, get the mean, and multiply by the area. So that will give you the volume of this cell. Okay. So to get the volume of the next cell, you will repeat the same procedure. Let's say for that cell, but this time you'll be using H3, 4, 5, H3, 4, 5, and 6, multiplied by the areas which is given there. So if you have a series, or if you proceed that, okay, if you can either calculate them individually, or you could use a simplified sort of a formula. Okay, which simply says A over 4 is the area of each cell. You sum of all the H that you use once and all the H that you use twice, multiply by that. All the H's that you use thrice, you multiply by 3, and all the H's that you use 4 times, you multiply by 4. So you can actually calculate it in one go, rather than calculating the individual cell. Okay, so I think I've got one example of this. Okay, look at this example. We have 1, 2, 3, 4, 5 cells. Okay, we've created a grid size of 10 by 10 meter, and the numbers here represent the difference between proposed and existing. So by the way, before I forget, if the number here is negative, that means it's a fill. Okay, so in this case, all positive, so it's a cut. Alright, so if you use that general formula, so area is 100 by 4. So now, the H that we're going to use once is going to be H1. We're going to use that when we calculate that figure there. When we calculate that, we're going to use H1. When we calculate this, we're going to use H4 also, only once. H11 will be used once, and H9 will be used once. Okay, as well as H8. So you're going to have H1, H4, 8, 9, 11. So 476, 810, 607 for H8, and 198 for H9, and 3554. So that is, those are the H's that we're going to use once. We use once. Next, we're going to look at the one that we're using twice. So if I just draw another hatching there. Look at this. If we're going to calculate that, when I calculate this figure, I use H2. Okay? But at the same time, when I calculate this figure, this volume here, I'm going to use H2 as well. So H2 in this case will be used twice. Okay? So H2, H3, H5, H10 will be used twice. So that's what we put in there. So they'll be used twice. Multiply by 2. Then the one that we use 3 times will only be H7 in this case. That one there. Because we will be using H7 to calculate that area. To calculate that, volume, that volume, and that volume. So 3 times. So that's where it is. 5.82 multiplied by 3. And lastly, we're going to have 4.77, which is H6. So we'll be using that number 4 times for that volume, that one, and that one. So that says, that's why we have 4 multiplied by 477. So that gives us 2394 meter cube. So that's how we apply the formula. Okay, but if you prefer not to, you can always calculate each cell, okay, individually. Okay. Okay, so that's a volume from spot height. Next is a volume from a contour. So contour that we've created in our detailed survey, in our map, in our plan, can be used because there are heights, height values, information on height. So we can use that information to come out with volume. Okay, when is it suitable to be used? When we have large volume, okay, such as volumes of water contained in a dam, a reservoir, soil heap, as well as if you do reclamation along the shore, cover a vast area. So using contour probably one of the best approach, the best method to be used. So the area of the contour surface is determined. So each contour line you have to determine the area that it contains. Okay, and you can treat that each contour line as a cross section, and you can find the area of a cross section using any of the method we've discussed earlier, either graphically or mechanically or using mathematics. Okay, so let's look at this figure here. So this is a map which has been overlaid over Google Map, just to show you the undulating, okay, the undulation of the area. So we've got like 3 hilly areas there. Okay, 1, 2, 3. I think I ought to change color. I just read. Okay, we've got 3 hills there. Supposing that I want to flatten this area for some development, I want to make it level. So let's say I want to remove this hill there. Okay. So what I could do is, if I can come up with the area of that contour line, okay, and the area of that contour line, so I've got one area there, and I've got let me use blue, and another area there. Okay, so we can say, or we can imagine that this is area 1 and this is area 2. So if I take the mean between A1 and A2, multiply by that distance there, the height, I mean, the difference in height between the area and the area, which is basically your contour interval. Okay, we can derive, we can get the volume of the area, or of the soil that need to be removed. Yeah, I think the next one probably explain it better. Okay, you look. Okay, you've got an. Let's say this is a piece of an area that we have to move, remove. I mean, okay, it could be for a particular purpose, maybe for underground storage or whatever. Okay, and the dotted lines represent the contour lines. Okay, so if I get to split those 4 layers into like that, we got 1 layer there, 2nd layer there, 3rd there, and the 4th layer, and each of the layer would have a cross-sectional area A1, A2, A3, and that would be A4. Okay, so the A4 represent the cross-sectional area for that particular contour. Okay, A3 will be for that contour, and so forth. So if you assume, or let the area is given by A1 to A4, the area of this contour line at each level, and if the interval is L, okay, then we can simply either use n areas if we want, or we could use prismoidal. Okay, so we can still apply, okay, the n areas, or the prismoidal, when we're dealing with contours, finding volumes using contour, which I say is suitable when we're dealing with a large area. Okay, so that's another example to show how we can apply the concept. In this case, we have contours going that way, from high to low. Okay, from low to high, I mean, and that blue line represent a river which flows that way. Okay, so what they propose, they're proposing a dam, going to build a dam there. Okay, and the water will be contained behind the dam like that. Okay, and we want to find out the capacity of the dam. Okay, so I've got one example there. Okay, it looks something like this. Okay, that will be the contour line. If we feed it with water, we do a dam there. So that will be the water that we are interested in. Okay, we can either use n areas, or we could use prismoidal, okay, to calculate the volume. Okay, I think I've got one example exercise that we can do together. Okay. Okay, let's look at that figure using the example previously. Okay, if the contour level are given there, and the area of each contour surface is given there, okay, calculate the volume of water in meter cube. Okay, so by utilizing all the A's, and all the E's in here, the contour level and the area, we can calculate the volume. Okay, the next page shows the solution. Okay, you can go through this, okay, in your own time, but now I'm going to basically explain. Okay, I'm going to use n areas. So I will sum up all the A's from 2 to 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, from number 2, excuse me, to number 8. Okay, and I've got that. And I multiply by 2. Okay, and plus A1 and A9. So that's multiplied by 2, so I'll come up with the volume. Okay, that's the total. Apply the formula, put the total in there, so that's the volume. Okay, that's by using n areas. Okay, using Prism model, a bit elaborate. We have to sum all the even, which is that one there. We have to sum all the odd, which is there. And here, we're going to use the equation, the formula. First area plus last, which is that one and that one. And 4 times even plus 2 times the sum of odd, which is 4 times that plus 2 times that. So give us that one there, 288, 240. We're going to sum all that. We get 318740. Apply it to the formula, L over 3. So we'll come up with this. We obtain that answer, or that number. Okay. It won't be exactly the same because they're both different methods. Okay, but you could see that Prism model, the number is a bit bigger. Okay, but if you look at the differences, it's only at about less than 2,000 meter cube, and we're dealing with 500,000 here, 500,000 meter cube, which is negligible. But the bottom line is when you do volume calculation, we are estimating. So do not just do one method. You have to do another method just to verify that what you have obtained is the best estimate that you can come up with. Okay, so that will be an example, or that's how you go about calculating volume if you're using the contour method.
انضم معنا الآن واشترك بالقناة ليصلك كل جديد. YSAG، معا نحو مستقبل مشرق.